12.
Yeah.
Can you tell me what it says? We'll do it together.
Given E equals 125.
Say it again. Just, you can just read it to me. I'm sorry, I'm trying to listen, my ears aren't that good.
Given E equals 125.
E equals 125.
Yes. Cosine 6 pi times 10 to the power 6t.
6 pi times 10 to the
6.
6t
Yeah.
minus
0.08 pi y
pi y.
in the z direction,
Uh-huh.
and h.
Volts per meter?
Yes.
Okay.
And h is 2 cosine 6 pi.
Right, okay. Times 10 to the 6t minus 0.08 pi y. And this is going to be AX, is that
Yes.
right? And this is amps per meter?
Mm-hmm.
Okay. And the question? This is the standard waveform in the time domain.
Find mu r and epsilon r.
All right, they're looking for the intrinsic parameters of the media. They're looking for mu r and epsilon r. They're wondering what they are. Now the key to this is two things. You see how there's no e to the minus alpha y? You all see that, class? There is no decay coefficient there, isn't that right? You all see that? Let me put a few things down here. What is the direction of propagation, a unit vector in the direction of propagation? Take a look at that and give me a reason for it. Go ahead.
It's 125 cosine e.
Pardon?
125.
Is,
120.
no,
times
the
5%.
direction of propagation. You all hear me? Okay. Direction of propagation is which way is the wave moving? Anybody?
Positive y.
Sure. And what she did is look right here at the coefficient of the spatial component inside the argument of the cosine. Y'all with me? So she knows that's beta, right? A minus value indicates it's moving in the positive y direction. So here, the unit vector in direction of propagation is AY. I want to make sure everybody understands that. Now, the phasor form of this waveform, I want to put the phasor form down. And this you have to know. You've got to know this like the back of your hand. There can be no uncertainty. The phasor form of this would be same magnitude, all right? Then it would be E, and you would just have this to the minus J right here, 0.08 pi y, and it would be in the AZ direction. Y'all follow me? That would be the phasor form. How many? Yes, sir.
The 125 should be 120 times pi.
Oh, I'm so sorry. Is that what you? 120 times pi. My bad. 120 pi. My ears aren't that good. I'll try hard. Y'all with me, class? Does everybody understand why that's the phasor domain form? This would be, technically we'd put this, if you were in Gross's class, he would make a real stink about that if you didn't put a tilde over it. See, I don't do that. The reason is, if I see a J, I know I'm in the phasor domain. I can't be in the time domain. They don't exist. Y'all with me? That's the way I do it. All right, now he wants these things. So you correctly identified the direction of propagation as AY. Does everybody follow me on that? Positive AY. Now the next thing we need to do is figure out how do we get these values. And you all see there is no e to the minus alpha, in this case, y, is there? There is no decay, so we know it's lossless. Y'all with me on this, class? So it's lossless because alpha is non-existent, it's 0. Since alpha is 0, we can say it's lossless, right? After that, we know if it's lossless. Now, I've done some stuff, but I want to just make sure everybody sees this. And remember, this you have to really understand well. If you don't, you get in a lot of trouble. Remember, the propagation constant is alpha plus j beta, and it's equal to the square root of j omega mu times sigma plus j omega epsilon. That's the general form, right? But it's lossless, right? And if it's lossless, the alpha goes away, and so does the sigma. So you get j beta is equal to simply what? J times omega square root of mu times epsilon. This is if alpha is 0, which means sigma is 0. Now I want you to look at that and convince yourself. Just set sigma equal to 0 here, right? Then I have j omega squared. The square root of that is j omega, right? Then I have mu times epsilon left over. Y'all follow me?
So we know that sigma and alpha are 0 because of.
We know alpha 0, right? By looking. Y'all follow me? By inspection. And if alpha is 0, sigma must be.
Gotcha.
If sigma is not 0, then we have a positive value of alpha. Y'all follow me on that? So that's the way we always inspect these things and then instantly know. Now when you look at this further, y'all see, again, my point is if sigma is 0, this is what happens, right? Or if alpha is 0, this is what happens, either one. Agreed, class? Now, if you're at that, let me keep going on this line. I'll forget J and I have beta is equal to omega. Here I break it out as square root of mu naught epsilon naught times square root of mu relative epsilon relative. Now please just follow along. Y'all agree with that? Because mu is mu naught, epsilon, mu relative. Epsilon is epsilon relative, epsilon naught, right? And what am I going to replace that square root of mu 0, epsilon 0 with, anybody?
Over C.
It's sure, it's just 1 over c, right? C is the velocity of light in free space. And then I have times square root of mu relative, epsilon relative. Here it becomes pretty straightforward. Do I have beta? Obviously, right? It's the coefficient of that y inside the cosine argument, right? So I go ahead and I set that equal to 0.08 pi. Y'all agree with that? Now, by inspection, also what do I have in terms of omega? You should be able to take one look and tell me what omega is. Class?
6 pi times 10.
Sure, it's 6 pi times 10 to the 6th, right? It's equal to 6 pi times 10 to the 6th. And that would be, the units are radians per meter, but I don't even bother with that. Unless we do degrees per meter, I always default to radians per meter. Then after that, I mean, if I wanted, I could get F, right? I would divide that by 2 pi, correct? And that means it's 3 times 10 to the 6th hertz if I wanted it. Now I have omega. So now I'm going to go down here and I'm going to say, really, square root of mu relative epsilon relative here is equal to c, or 3 times 10 to the 8th. I'm going to multiply by c both sides. And then I'm going to divide by omega. And omega was 6 pi times 10 to the 6th times, and this is going to be times 0.08 times pi. And that gives me mu relative epsilon relative multiplied together, right? What we could do if we wanted to, we could say this squared would be equal to mu relative epsilon relative, right? I don't need to be going too fast on this, but you follow the steps here, it's pretty self-evident, right? Remember, this stuff is like, should be second nature. Just remember this. It should not be any concern when you do these problems, when you get done with it. Go ahead.
Where did the 3 times 10 to the 8th come from?
That's C.
C.
It's 1 over square root of mu naught epsilon naught is C, so the inverse would be 1 over. That's it. And I'm using 3 times 10 to the 8th. I'm not using the exact value. Just for everybody, C is the speed of light, and I'm approximating it as 3 times 10 to the 8th meters per second. Good on that? Now that's one equation. We still have 2 unknowns. We need another one. What did I tell you last time about ratioing of E and H? What is it equal to, class? The intrinsic impedance of the media, correct? Everybody? You with me at that? And what is the intrinsic impedance of the media? In general, it's equal to square root of j omega mu over sigma plus j omega epsilon, right? That's the general form, correct, class? How many remember that or saw it? Yeah, at least rings bells, right? This you're going to have to know too. Now this is the general form. Now what did I say here? What did we say about sigma? Its value was?
0.
0, so it goes away. Now take a look at this. You see how the j omegas go away? Everybody? So that means in a lossless environment, your value for eta is just square root of mu over epsilon. I'm going to expand that further. Y'all with me? Now, to expand it further, it's equal to the square root of mu naught over epsilon naught, square root of mu relative over epsilon relative, right? And here I'm just plugging in, right, class? With me? Now, what is the square root of mu naught epsilon naught? I call that the intrinsic impedance of free space, right? What is that value?
125.
Right, 120 pi ohms, or about 377. Correct, class? I'm trying to answer your question, but I want to go through a whole bunch of things at once. Make sure everybody sees the relationships. These are things that are, it's like teaching circuits and assuming everybody understands V equals IR. If they don't know that, everything else is a wash. You can't do it. And it's the same way here with these basic concepts. You have to know them all. Now, I'm going to go down here and just say, well, this is equal to 120 pi times square root of mu relative epsilon relative. Now, there's one real important thing we're about to do, and some of you know it. The coefficients here and here, and I should say 120 pi, these two, the ratio of the two will be the magnitude, right? The magnitude ratio of e to h will be this value, won't it, class? Everybody with me on that? Magnitude of E over magnitude of H. And think of the units. E has the units of volts per meter. H has the units of amps per meter. Volts per meter over amps per meter is volts per amps. A volt over an amp is an ohm. So it'll always work. That means this right here is ohms, and it's equal to the ratio of E over H, which just happens to be 120 pi over 2. Y'all with me? And here I just took the coefficient here of the cosine, which is the magnitude of E, and divided by the coefficient of the H field. Y'all with me? The cosine. How many see what I'm doing here? Got me on this? All right. Now, this is kind of nice, isn't it? Just work with me right there. What am I going to do? Take a guess.
Divide by 120.
Get rid of 120, right? Get rid of it. So if I do that, I have square root of mu relative epsilon relative is equal to simply 1/2, correct? Y'all agree with that? And then what am I going to do? Square both sides, right? And in doing so, now I have mu relative over epsilon relative is equal to 1/4. Here, I have mu relative over epsilon relative is that. Let me see if I can simplify this a little bit. Y'all agree this pi can cancel in here, class? Just trying to make it a little easier to see. Y'all with me? All right, what about the 3 and 6? 1/2, class? Yeah. I'm gonna make it 1/2. And then 8 by 6, 10 to the 8 by 10 to the 6 is 10 squared, right? Or 100, 10 squared. .08 is really 8 divided by 100, isn't it? So make that 8 divided by 100, or 10 squared. Get rid of that. You don't have to do it this way. Y'all with me? Then I have 8 by 2 is 4. 4 squared is 16. So now I know my mu relative, epsilon relative is equal to 16 over there. And the ratio of the two is 1/4. So pick your poison. What do you want to solve for first? If I solve for mu r and have 16 over epsilon relative, all right, for mu r I have 16 over epsilon relative squared is equal to 1/4, correct? I'm just plugging numbers here. You agree with me? Now, at this point, I don't care how you do it, you can cross multiply, so I have 4 times 16 equals epsilon relative squared, right? Take the square root of both sides, we get epsilon relative, right? Would be 2 times 4 or 8. You agree with that? I hope I'm doing, y'all follow, I mean, you asked about this, I'm just trying to show you the way I'm doing. And if you got this, what do you know mu relative is? Just look. 2, isn't it, class? Okay. I want to tell you one other thing about these things. Sometimes you're not going to see exactly what to do. Go for what you can get. Go for what you know. Remember that. Because these problems, the more you do, the better you get at it, and then they'll become automatic. And you'll know this stuff, really know. But you got to do, I assign problems, but if I was you, when I was sitting where you were, what I used to do is every single problem in the back of the book if possible. I mean, usually we had odd answers. Occasionally we had the solutions, man. I do every one. If I didn't get the answer, I'd ask about it. Now, it takes more time, but I'll tell you, you develop a high level of confidence in understanding and knowing what to do when anything comes at you. And you get real high grades. I'm being honest with you about this, okay? Don't try to just kind of know. You really need to immerse yourself. How many did that problem? I mean, the solution's there, but do y'all follow the thought process, right? You asked about, did that answer your question? Is there any other part of that problem?
No, that answers it.
Okay. Anything else? Good question.
Could you work 6.22, please?
Yeah, you're gonna have to tell me what it is, but let me erase the board first. I've always felt with working out problems after you try, even if you got the solution, you don't understand, is a good way of really exposing how the actual formulas work and are applied. Anybody have any news about university policies with COVID or anything like that? I haven't got anything.
I haven't heard anything.
As far as I know, football is going to be football, as far as I know. Don't quote me on it. Go ahead, sir.
I'm trying to find it.
622, did you say?
A semi-infinite slab exists for z greater than 0 with sigma equal 300 capital S divided by m.
300 what?
S divided by m.
That's Siemens per meter. I like to put 1 over ohm meters because you're used to ohms. Okay, go ahead.
Epsilon r equal 10.2 and ur equal 1.
Uh-huh.
And then at the surface z equals 0. And then
Wait, E equals what?
z equals 0.
All right, at Z equals 0, what is the E field?
1 cosine pi times 10 to the 6 t.
Hold it. E equals 1 cosine, go ahead.
Pi times 10 to the 6 t.
Right?
Ax volts over meter.
All right. Now this is one of these problems, this is a Whitworth problem. First of all, you see that, you say that wave ain't propagated. Here's the thing, he stipulates that's only at the surface right here. He's saying right here, in other words, if Z was 0, this is what we'd see. Y'all follow me? Well, if Z is 0, beta Z here is 0, so you wouldn't appear in this argument. Y'all follow me, class? This is a Whitworth problem. All right, now what does he ask for? The E field anywhere in the slab, or?
E and H, anywhere in the.
What's that?
E and H.
Okay, so what he wants really is both E and H anywhere in the slab, and he wants it in the time domain. Here's the way I'm gonna go about doing this. This is not gonna be hard. The key thing is getting 2 parameters. The propagation constant and the intrinsic impedance. Y'all hear me? Before we do that, we have to be able to ascertain the frequency of operation, or omega, by looking at this. Not the front row, guys. Somebody in the back. What's omega by looking? Anyone in the back?
5 times 10 to the 6.
Yeah, and what you're really doing, well, it's pi times 10 to the 6. It's the coefficient of t inside the cosine argument. Do you agree with that? So that's going to be pi times 10 to the 6. And that's radians per second. And if we wanted F, it would be what? 1/2 times 10 to the 6 hertz, right? Just putting them both down for you. Agree? All right, now that we have that, 2 things I want. Propagation constant and I want intrinsic impedance. Remember that. Once you get that, everything else falls apart. But you have to have both. So can we get both? First, the propagation constant, the square root of j omega mu times sigma plus j omega epsilon. By the way, what I recommend is, if you ever are uncertain if it's a good conductor or a lossy dielectric, just run the equation. You can't miss. You got expensive calculators. This is a no-brainer. Follow me? You do that, you're going to get a real and imaginary part. And the second is the intrinsic impedance. It's the square root of j omega mu over sigma plus j omega epsilon. Now hold on for 1 second. I'm going to put these values in, but I want everybody to appreciate what I put down there. Both of these are going to be complex. They'll have a magnitude and an angle. The first one is the important one, in my opinion. That's going to have alpha plus j beta, correct, class? Now, if you look here in that equation, mu relative is 1, so I can just make mu in this first equation mu naught, right? And in case you're wondering, mu naught is 4 pi times 10 to the minus 7th henries per meter. Make that mu naught there. Now the second thing gets a little hairy. I've got a value of sigma of 300 and epsilon relative 10.2. I'll show you what people will do. You don't have to do this, but this is what they'll do. What they'll do is they'll take sigma as 300, and they want to compare that to omega epsilon relative times epsilon naught. And epsilon naught is about 8.854 times 10 to the minus 12 farads per meter. So they're going to compare these two. We got the 300. We've got omega as pi times 10 to the 6. We have epsilon relative is 10.2, and I've got epsilon naught there. Can anybody tell me what this value is if you've got a calculator? And please bring your calculators if you don't. If you don't have them, bring them. It helps sometimes because I'm going to tell you things you should be able to calculate fairly quickly for quizzes. I know some people don't like it. This is the way I would do it. Now, you don't have to do it this way, but it may save some work. What am I trying to do? I'm trying to figure out if it's a good conductor, right? That's big. Or a lossy dielectric. Or I should say a low loss dielectric, if that's big. And if it's about the same, then I got to run the whole number. Anybody? You got it? Well, you're going to have to read it to me. I don't know.
5.6 times 10 to the negative 5.
This is 5.6 times 10 to the minus 5.
Yes.
Anybody confirm that? I believe you, but I just want one more person to confirm. Anybody?
Confirmation.
Come on. Anybody else get that number? Anybody else? I just want to know what this is. So if you take pi times 10 to the 6 times epsilon, yeah, that's about right. I bet you $1 it's right. You get it? Anybody?
No, that's not right.
It's not right. Somebody wanted $1. Go ahead.
I got 0.00028.
0.00028, did you say?
Yes, sir.
All right, now we're going to stop there. Let me just make this point. You see how much bigger this is than that? All right, so it's much greater. Now, you don't have to do it this way. That would make this a good conductor, wouldn't it? If sigma is much greater than omega epsilon, right? You know this is a good conductor. Even if you don't, you can put all the numbers in there. Y'all with me? But if it's a good conductor, what did I tell you last time? Does anybody remember about alpha and beta for a good conductor? They're the same. As a matter of fact, alpha equals beta equals square root of pi f mu sigma, right? Isn't that right? Correct? Or really, this is what? That's omega over 2 if you want. You got omega right somewhere. And so if you take pi over 2 times 10 to the 6, right? times mu, which is just mu naught, times sigma, which is 300, you can give me this number. Somebody can give me this number. Do you agree with this, class? And if this is not making sense, ask me, and I'll try to respond. I'm trying to make sure everybody sees this. I don't want to spend a lot of time in the weeds doing little math, but trying to get through this and make sure everybody sees. What do you get for this? Anyway.
I got 24.33.
So anybody confirm that? 24 point, say it again?
33.
3. And this would be Napiers per meter, right? Or radians per meter, either one. And the units you're gonna see are gonna be identical in terms of their effect. Are you with me, class? How many else, anybody else get that? You got it? Okay. Now, if that's the case, let's get this one too. And by the way, since sigma is so much greater than this, we can just say this is what? That's square root of j, which is really e to the j 45 degrees if we want. We can just, or j pi over 4, because j is 1 at an angle. E to the j pi over 2. Do you remember this from last time? Square root of that is e to the j pi over 4. And then it's going to be times square root of omega mu 0 over sigma, right? If it's a good conductor, because sigma is so much greater than omega epsilon. Do y'all agree with this, class? What do you get for this? Please give me a hand with this one. I'm really trying.
I got 0.11
For this,
times, times the e to the
okay,
j term.
0.11. Anybody confirm or deny? There are no wrong answers. You got that?
Yeah.
How many got that? Well, you did, right? Anybody else?
I got 0.11.
Okay, good. We're gonna leave it at that. Y'all follow me? Now that we have these two values, he wants the electric field, right? And he wants the H field as function of position and time, correct? Now we've got the E field as a function of position at z equals 0, correct, class? Please watch. So if we want it in general, I'll write it over here. I can say the E field, I know it's gonna have a magnitude, which is 100, right? Then it's gonna be cosine of omega t, which is pi times 10 to the 6t, minus beta z. Now look, you got the beta as 24.33, don't you, class? With me? So it's minus 24.33. The direction it's propagating is z, so it's times z. It's in the AX direction. And I forgot one thing. What did I forget? Anyone?
Attenuation.
I forgot to put in e to the minus alpha, right, times z. And I'll do that right now. So instead of 100, I'll first put in e to the minus 24.33 z here, and then I'll put the 100, and that's the E field. Now, I don't know the form of the E field he has, but that's right. Y'all with me? Now, you can put it in terms of a sine. Remember, sine and cosine are related by, what, 90 degrees? You could add and subtract the pi over 2 and put it in terms of sine, depending on sign you wanted out in front. But this effect, this is the spatial temporal variation of the E field. Y'all follow me for a plan? How do I get H? Let me show you this in terms of, I'm going to assume you've got this down. I want to do it in the phasor domain first, because I want to make sure we're clear on this. This is important. So, if I wanted the phasor form of the E field right there, I would say the vector phasor form would be the magnitude, 100, right? It would have the e to the minus, let me just put alpha equal beta equal 24.33. So I don't have to write that over and over again. E to the minus alpha z Then it would be e to the minus j beta z, the beta's up here, in the ax direction. Y'all follow me? That's the phasor form of the E field, correct? Please watch this. This gets a little bit confusing if you're not careful. I gave you a couple equations that relate E to H and H to E for plane waves. Y'all remember if you wanted the H field, if it was a plane wave, it would be in the phasor 1/eta, right? And then it would be unit vector and direction of propagation crossed in the E field, right? Y'all remember that? How many do? There are two equations, that's one of them. Does anybody remember the other equation? Anybody? What is E, huh?
Isn't it eta times?
Well, minus, minus, you're right, go ahead. Eta times
The or the.
unit vector and
Yeah.
direction of propagation crossed into,
The H field.
right, and this always works for plane waves. Remember that. Doesn't work in general for near fields and stuff, but it works for waves that are propagating a long way away from the source. Good on that, everyone? All right, let's keep going on this. So, back to this. Please watch this. This gets a little tricky. Now, when I do this, what I'm going to do is say this is 1/eta. You remember eta for R's was equal to a magnitude of 0.11, I believe, approximately, right? But it was at 45 degrees. So go ahead and put e to the j pi over 4 here. I'm leaving it in the radians, okay? Y'all with me? Then it's a unit vector in the direction of propagation. Which way is this wave propagating, people? Take a look. Class? Positive z, right? So then you put in az, then you cross it into the E field. Well, that's the E field. I'm going to write it down for everybody. Please hear what I'm about to say, because this is where people make mistakes. This is the phasor. Y'all agree with this? And I'm literally following the formula. Now, when I do this, what I'm going to do first off is get the constants up in front. You see this as 100 is a constant, correct? It's divided by 0.11. Don't worry about the value. So I take 100 over 0.11. That's right off the bat. Next thing, I have e to the j 45 degrees or pi over 4 downstairs in the denominator. When I take it to the numerator, what happens to the angle? Minus, doesn't it? Sure. So that means it's e to the minus j pi over 4 or 45 degrees. Y'all with me? How many see this right here? Real important. Do you see it back there or not? If you don't, let me know. I want to make sure I can get to you because this tricks people all the time. It's the little things that hurt people. Now, after that, I've taken care of the 100, this, and this. Next thing I'm going to do is just pull this out. This is a strict real number, e to the minus alpha z, right? And alpha's up there. I'm going to leave that there. That stays there, right? E to the minus j beta z. I'll combine a few things in a second, but y'all with me what I'm doing here. And finally, I got to take care of az crossed ax. What is that? Z crossed x is, and here's the way you do it, yeah. If you're going in this direction, they're all positive, right? So it was z crossed in x is positive y. Y'all follow me on that? It goes in the opposite direction, it's negative. So it's positive ay. The units for the H field would be amps per meter. This is in the phasor domain. But I want to do one thing for everybody's sake. See how there's those J's there? What I'm going to do is combine them and say this is going to have a magnitude of 100 over 0.11. And then I'll leave the e to the minus alpha z out front. And I'm going to have e to the minus j. And then it's going to be beta z here plus pi over 4. and it's in the AY direction, amps per meter. You good with that? Now that's the phasor form of the H field. I don't know if Whitworth gives that in this problem or not. You can give me the magnitude of this, I don't know what it is. It's a little less than 1,000 it looks like. Anybody tell me what this is? 100 divided by 0.11 approximately.
909.09.
909 is good for me, all right? We're gonna just call it 909, okay? We know we got alpha and we've got beta. That's in the phasor domain. Do you remember how we get the time domain form? I mean, the technical formula is what? H in the time domain as a function of zt would be the real part of e to the j omega t times h vector phasor, right? Isn't that the formula I've given you before, class? But really what I'm going to do is what? I'm going to take these two terms, I'm going to get a cosine form is what I'm going to get. Am I not, class? Y'all remember that? What's going to come out of this is this. Same magnitude, 909 approximately. E to the minus alpha z, that's fine. Now, this is the part that I have to expand in cosine plus j sine, right? And I multiply it by e to the j omega t, and when I take the real part, I end up with this. Cosine of omega t, omega's back there, it's pi times 10 to the 6th, but it's going to be minus beta z minus pi over 4, isn't it, class? And the reason it's minus pi over 4, because see how these two things, with the minus j there? When we expand and take the real part, it'll boil down to this, and that's AY amps per meter. I hope I answered your question. And who asked this? Is that the answer consistent with his in the book? Anybody?
Yeah,
Yes?
it is.
Okay, but that's the way you do it. Now, and the thing I want you to understand is the phasor and the time domain form. You got to understand both of these, because the phasor form is the way to get the time domain, to be honest with you. It's the easy way, okay? Any other questions about the whole? Yes, sir.
How did you go from the phasor domain to the to the cosine omega t?
Okay, what I really did here, and I took a shortcut, when I have e to the j omega t times this, I just want you to watch it. E to the j omega t times e to the minus j this is one big number where I have e to the j omega t minus beta z minus pi over 4, right? That will break up into a cosine of that argument,
Okay.
minus j, j plus j sine of that argument, right? The cosine's the real part.
Okay.
So I just maintain the cosine. With me, class?
And that other part just fell?
Well, you only get the real part when you're in the time domain. The imaginary part gets killed. Okay? Yes, sir.
Do we need to find the E field too? For the,
We have the E field right here, don't we? It's there and then right here. See it?
okay.
I mean, and I put it in the phasor domain right there.
Okay.
All right?
Alright, that's where I got confused on that.
All right, everybody good with this? How many looked at that problem? The thing about this problem is a lot of this gets a little just boring, and you gotta force yourself to go through it. If you don't, you're really gonna be wishing you did later. All right, now I need to go ahead and with the time remaining, get into stuff. Well, get into some stuff with current and conductors. These are great problems to really showcase important concepts. Now we're going to talk about what happens in good conductors. Specifically, there's a thing called the skin depth, and then what happens to the resistance of wires and why it goes up, becomes so high in AC circuits. That's the real thing. So bear with me and stay with me. So first, we assume we're in a good conductor. And a good conductor means sigma is much greater than omega epsilon. Factor of 100. That's what I sort of look at. Some people say factor of 10. Let sigma be 100 times omega epsilon, all right? With me? Now, after that, if we're in a good conductor, and we take a look at gamma, it's equal to square root of j omega mu times sigma plus j omega epsilon. But because of this, gamma is approximately equal to square root of j omega mu times sigma, right? I'm just doing it again. And that means here that this is really alpha plus j beta, or simply, in this case, it's going to be 1 plus j times the square root of pi f mu sigma. I've done this before, and it really means that alpha equals beta equals the square root of pi f mu sigma. That's all it is for a good conductor. We've done this before, I'm just rewriting it to bring you back so you've got a starting point. Now, if that's the case, and here, just listen. If you had an electric field propagating in the z direction, so this is the direction of propagation, we have an electric field here, E, it's going to have a phase, call it E naught, e to the minus j beta z. The phase doesn't affect the magnitude at all. Do y'all follow me? Phase like e to the j 45, e to the j 0, e to the j 100 degrees. The magnitudes, all those are 1. Do y'all follow me? So what we usually do is plot the magnitude of that times e to the minus alpha z. Now this is where it becomes important. That alpha tells you that the further in you get, the smaller the magnitude of the electric field component. It's decaying exponentially. Y'all follow me? I just want to take a look at the maximum value of the envelope. So there comes a point right here where you're at what's called the skin depth. All right? That's the symbol for skin depth. Listen to me now. You don't have to write this down yet. This is the point where the electric field becomes E naught e to the minus 1. You follow me? And now in your mind, you know that means that alpha z equals 1, or alpha times the skin depth is 1, or the skin depth is equal to 1 over alpha. That's how they get it. It's 1 over the square root of pi f mu sigma. That is the skin depth. It becomes very important. It's the value that gives you an idea. About 33% of the field's value is left after that point. The waveform is down to about 33%, its original peak, all right? This is real important. So, how do we use it? We could use it a lot of different ways. Wentworth-Spokey talks about a couple. Here's what's really used. It's in resistance calculations of wires. So when we talk about wires, and I like to do it this way because this has got a lot more meaning. It's really applied right here. When I talk about wires are good conductors to you, right? You connect things to make them work electrically with wires. They're not supposed to be high resistances. When you have a wire, if you have a wire with a radius A, and it has a length L, has a conductivity sigma, then the resistance between this end and this end are, if we talk about the DC resistance of that wire, it would be proportional to the length, inversely proportional to the cross-sectional area, or pi a squared, and inversely proportional to sigma. How many remember that? Remember when you had EMAG 1, they talked about resistance, and resistance was always proportional to the length of the conductor. Longer, the more, right? It was always inversely proportional to cross-sectional area. Think of it as resistors in parallel. The more in parallel, the less the resistance, right? That's what A is. And it was also inversely proportional to the conductivity. For copper, the conductivity is what? About 5.8 times 10 to the 7th. That's enormous, right? Copper has very little resistance in wires, usually. For something like air, do you remember what I told you air was? Anybody? Sigma was about what? 10 to the minus 14th, 10 to the minus 15th. Just about nothing, right? So these gives you magnitudes of conductivity difference. But that's the DC resistance. Y'all follow me? Now, the AC resistance is a little different, so write this down. When I talk about AC resistance, well, at low frequencies, it's that. But whenever the skin depth is actually, sorry, I got this wrong. When the skin depth is less than the radius, when the skin depth is less than the radius of the wire, now think about it. Now the electric field can't penetrate into the wire. If you think about it, when you have current flowing in a wire, you really have this very small, immeasurable electric field on the surface, but this decays into the wire, and it basically, if you're at DC, it's the same value of the electric field all the way through the cross section. Do you remember when you did your DC problems, you assumed the current, and then you got J equal to what? The current divided by the cross-sectional area, right? And you remember you set that J value equal to sigma E, then you got E and you integrated it and got the voltage and you solved the resistance, right? If you don't remember exactly, just trust me. Well, I was assuming there was no change in the electric field throughout the wire in the depth as you go towards the center, but there really is. There's a big change if this happens. And all of a sudden, if the skin depth is less than the radius, especially a lot less, then all of a sudden what happens is all the current conducts through the outer layer of the wire. Do y'all follow me? It's not able to get down to the center. So if we looked at the cross section of the wire like this, if this is radius A, now, and this was a skin depth, I'll get out of your way, here's where all the current is flowing. It's just flowing in one skin depth. There can be, I can go formal proof on this, but it kind of defeats the purpose right here. All the current is going to hug the surface of the wire. Y'all follow me? And if that's the case, that means the AC resistance, if this is the case, then the AC resistance will be still proportional to length. Has to be. And it has to be inversely proportional to sigma. That has to be that. But now, where is the area the actual current's flowing? It's a greatly reduced area, isn't it? That area would be the total area. It would be pi a squared, right? That'd be the whole thing, but then I have to subtract off that inner area. Let me say that again. I take the entire area, pi a squared, then I gotta subtract off that inner area. What remains would be the area the current flows through. Well, that inner area would be what? Minus pi, not A, or not skin depth, it would be I minus this, or A minus the skin depth squared. Take a look at that and see if you agree. I'm gonna simplify it in a second. Y'all agree with that? Sure, right? Now, go ahead and I'll simplify it right here. That means the AC resistance technically would be this. L over sigma. Now I would get pi. I'd see the A squareds cancel, and I'd have pi times 2A delta minus delta squared, skin depth squared. This is what this is just simply blowing this thing up, pulling out the pi, and you're left with the A squareds cancel. You get a 2A skin depth from the inner product right there twice, and then you get minus gamma squared. But I'm going to tell you, in most cases, or when the skin depth is much less than A, then the AC resistance is simply equal, and this is the way it is in 99% of the problems we worry about, over simply 2 pi A skin depth. Now let me explain something. This right here is really the perimeter. It's like this. You take a look at this thing and assume it has a radius A and a thickness of a skin depth. Just listen to me. You with me? Now take that, cut it right here, and just peel it into one long piece. All right, what's the circumference of a circle? 2 pi times the radius, right? Or the perimeter of circumference. So this dimension would be 2 pi A, and the thickness would be this, and now that is the area the current has to go through. Y'all follow me? That's the AC resistance. I didn't get to a few things I wanted to get to today. I'm gonna be going through, just for everybody's sake, I'm gonna be going through, power, which is coming up. And then I'm gonna go through polarization next time, I can't do today. And then reflection off of, boundaries. And a lot of this is you're gonna see similarities between this and what you did with transmission lines. So, sorry for slowing down, but I appreciate the problems. They were important for everybody to see this. Thank you.